Hi there, and welcome to the DynamoDB corner of the Amazon Web Services YouTube channel. I'm your host, Sean, and I'm a DynamoDB Specialist Solutions Architect. I'm coming to you from my office in Dallas, Texas, to present part 2 of a 2-part series on best practices for DynamoDB. If you haven't watched part 1, go and find it first and watch that before you watch this video. This video covers the topics of security, logging, limits, and bulk data updates. We're going to pick up where we left off, service quotas, formerly known as limits. I promise I do all I can to make this topic interesting. Let's get started.
Now, let's discuss everyone's favorite topic, service limits and quotas. It's the thing that gets me real excited. I get to Excel spreadsheet all my limits, track them in one place in a giant spreadsheet, which is actually what a lot of my customers do. And in this case, we're going to, of course, show you tables of data for this slide and the next one. And hopefully this is interesting. We're going to discuss some of the basic limits you need to know to be a good DynamoDB user. Now, the most common limit that customers will need adjusting is the table and account read and write capacity limits, aka the table level, account level throughput limits. These are limits in the provisioned mode. In case of table, it's how much provision capacity can be added to a single table. It also does account for the global secondary indexes, or in the event of an on-demand table, the table level throughput limit is how many requests a single on-demand table can process, either read or write operations. The default is 40,000 units. In the case of a provision table, the count level limits come into play, so you can provision up to 80,000 units. Now, these are soft limits. You can go up as high as you want, as high as you're willing to pay for. When you make a service quota, service limit increase request, please be very reasonable. If you need 1 million units, we'll get it to you. But if you just need 100,000, just request 100,000, either read or write, or read and write, whatever you need, and we will process that for you. These limits are available in AWS service quotas. Now, the other option that is pretty important to know, and these are really the top 3 limits, is the max number of tables. You're limited to 2,500 limits in an account. We could raise that to maybe 3,000, potentially more, but we like to have customers limit the number of tables per region. This is in AWS service quotas. If you need to increase it, provide your justification. And if you really need more than 3,000, you might be using your tables wrong. Or if you are following our best practices, perhaps you need to start making new accounts and kind of siloing them, the tables inside those accounts. At the end of the day, it's actually not hard to quote unquote cross account a DynamoDB table. It is very easy. You just assume the role, get the credentials. The latency is exactly the same from then on. Getting the credentials is the hard part, but once you have an access key and secret key, you can access Dynamo in whatever account in that region that you want. Monitor your keys and make sure you use least privileges, because at the end of the day, anyone with those credentials can access your table data. But thankfully, those are some of the most robust options for security policies, different ways to audit and monitor. And we'll be covering those a little bit later in this presentation. Right after this, we'll be going into the security portion. Now, max dial downs is the number of provision capacity decreases per day. You can have 27. That means you have 4 initial decreases. This is the default, 4 initial decreases. So in UTC calendar day, the first 4 will just be able to be done immediately. And then we limit you to 1 decrease per hour until the day rolls over. And when it's the next day, you get 4 more, which you will burn first. Once those first 4 are used, then you can do 1 decrease per hour. You can always increase your capacity, go from 10,000 to 100,000 units, but dial downs are limited to that number. There's not much utility for having fewer dial downs. I mean, DynamoDB meters your usage about once per hour. You can scale it up, you can scale it down the hour. You don't know when we're going to meter it. So, there's not much utility to lowering it, because it's not like it's, by probability going to save you more money. But in theory, we can increase this up to 50-something number of dial downs if you'd like. Diminishing returns there as to whether in your metered bill, the cost will be lower. Now, item size in Dynamo, by the way, this is the last, we have one more table after this, but stick with me. Thank you for paying attention. Dynamo items are limited to 400 kilobytes. This is a hard limit. If you need larger items, you need to break them up. We'll talk about that later. And then the number of GSIs, the soft limit limited to 20. If you want to monitor your limits, we publish your table limits and your account limits to CloudWatch under these metrics at the top. If you wanted to see how much you're provisioned, either by all tables or on a single table, you can use these CloudWatch metrics. So at the end of the day, you could create alarms, you could create CloudWatch graphs, not CloudWatch graphs, CloudWatch dashboards to show your account limits, or of course you could just export these to a third party if you'd like. I mean, there's a lot of different services that will pull CloudWatch metrics and then dashboard them differently, however you'd like. But these are nice utility metrics. By the way, if you want to figure out your percentage of usage, you can create, do some metric math in CloudWatch and do some quick division, say between your account limits, account max reads, and account provision reads. And be aware, these are for provisioned tables. So these are technically your table limit is your table limit for provision and for on-demand. But your provision capacity in the limit usage, this is all with the provision capacity mode. If you don't know the difference between those two, we will talk about that a little bit later on. Now, this is a slide for global tables. So if you have a global table, pay very, very close attention to what I'm about to say. If you increase the table write capacity on your global table at any point, the default is 40,000. If you increase it, before you do that, you must increase the max streams IOPS, aka maximum write capacity for a table with stream enabled. This limit defaults to 40,000, which, as you can probably imagine, matches the table write throughput limit. If you increase your table write throughput limit before you increase the max streams IOPS, you will receive an error on your global table when updating it. That will lead to a really, really bad day. Increase this limit using AWS service quotas, and then increase your table write capacity limit. The same will be said if you're adding a global table replica to a new region. Make sure that the max streams ops limit is already set. Make sure that then the write capacity is updated, and have them check the other limits that I mentioned earlier. Allow large indexes and allow large streams, which are mentioned here. Now, these are not well documented, and this may be one of the first times we're putting this in writing, and all of this is subject to change. This is just current at the time of publishing of this video. A GSI, we desire that to be less than 2,000 partitions. It can certainly be much, much larger. We have huge, massive partitions, massive global secondary indexes, that is, with many, many partitions. But if you want more than 2,000, you need the allow large indexes or tables flag to be turned on. It's a Boolean, false, true, by default, false. As well, if you have a global table, global tables need streams enabled. In order to enable a stream on a quote-unquote large table with more than 2,000 partitions, you must set the amount, you must get this done, and this will set the flag to true. You will have to answer several questions for both of these limits on the bottom. They're not in AWS service quotas. You may only hit these limits whenever you call update table if you're not aware of them. And the end result is create a service limit increase case. And they're not, these as of this writing are not in service quotas, but check now, they may be there now. All right, what are some important things to know for access and identity management? So what I will say is that in order to interact with DynamoDB tables, table data, caller control plane APIs, you need a signed request. Request credentials can come from IAM or STS, Secure Token Service. At the end of the day, you have an access key, secret key, and optionally or possibly required, depending on where you got your credentials from, a session token. And those are all included or used to sign the request or included with the request, and eventually makes it to the DynamoDB service. So DynamoDB APIs are protected by IAM. In addition, you can provide additional controls on top of those to further scope down permissions. AWS organization SCPs will limit permissions of identity policies. And the identity policies you could write something that says like, don't allow delete table. And then this would mean that no DynamoDB table can be deleted at any point, and this is a top-level policy that's applied regardless of what the identity policy says. Now, policies can support a significant number of conditions. You can do the following. Allow reads on an item identified by the partition key user 1234 on Sunday morning from 10 to 10:15 a.m. from IP address 1234, but only with the Java SDK v1. This is all possible with IAM policy language. In the event of the partition key, where I'll discuss that in a little bit, that uses what's called the leading key. The timestamp, there's a timestamp condition variable that you can use, saying only allow requests between a particular time range. IP address is called the AWS source IP in the IAM policy language. And then the user agent is accessible. And so you can say, give us only allow requests where the user agent is equal to X. Now, that's just an example. I don't think you write a policy exactly like that, but I just want to mention that the whole scope of the IAM policy language is available to you when you construct these identity-based policies. So when we construct policies, DynamoDB allows item-level access control or row-level access control. It's only based on the partition key using what's called the DynamoDB leading key. As you can see, we say that this operation can continue so long as the leading key is equal to that federated account ID, which is that Amazon.com user ID. With, I believe it's IAM, but it might be STS. I'm not 100% sure. I think it's IAM, but I really would have to check the APIs. You can get a federated login using an external identity provider such as Amazon or Google or Microsoft. And then that has a unique ID, which is passed back. And when you make it, once you get your credentials, you can call DynamoDB and only be allowed to access data under a particular partition key. Note, you cannot put a restriction on sort key. So if you write this policy, you can't say partition key X, sort key Y. Not possible. You're granting access to a particular partition key. Now, what this policy does, which is an example pulled from our documentation, is say that you can only modify or work on the specific attributes: user ID, game title, and top score. So at the end of the day, a user with this policy could update the game scores table. You can't see what the operation is, but let's say it's like put item for their user ID, really any item under that user ID. If it's a partition and sort key table, really any item. And they can only modify those attributes. And so that's the power of fine-grained access control. In addition, you could apply those other things like only being able to update on Sunday morning between like 10 and 10:15 a.m. All right, so be aware that when you write data, read data on a DynamoDB table, that table sits in exactly one account. The AWS account owns the resources created in that account. If you want to access resources in another account, you need a role. Then you can assume that role and make quote-unquote cross-account API calls to the DynamoDB table in the other account. From DynamoDB's perspective, if you have a set of credentials, we evaluate the policies. If access is granted, we'll allow you into the DynamoDB table to do the operations that you selected. DynamoDB currently supports, at the time of publishing of this video, identity-based policies. We suggest that you create policies that grant access only to the required resources. You can create policies based on application, based on the user. For example, the DevOps engineers can create and delete tables, but the developers can only call the data plane APIs like put item, batch item, and query. We suggest you look at creating roles and IAM groups. So IAM users can be put into IAM groups, and roles can have, as well as IAM groups, IAM users can all have managed policies. So if you create a policy, you can attach it to a role in a group, and you can say things like you can put item, get item, and so on. We suggest you consider fine-grained access control, but we admit that this is a fairly niche use case. Many applications will need to access most DynamoDB table items. They'll need to be able to update many attributes, and we can't know exactly which attributes will need to be modified at what times. So instead, you may want to write basic policies that say things like, you can write an item into this table so long as you're coming through VPC endpoint, or we can write at this item so long as you're coming from the corporate IP range. Note that users may come from different locations. The principals, the callers, may be on the AWS console. Perhaps on the AWS console, you don't want to allow scan or query. Instead, you're only going to allow scan or query if the user is calling from the application from a particular IP range. Be aware that you can get federated access, federated credentials, and then hop into DynamoDB. AWS Cognito through the user pools simplifies this process. You can use an external identity provider, such as Amazon or Microsoft or Google accounts. Once the user is logged in, you can assert their identity. The third-party service will assert their identity. They can get a credential. They will have a unique user ID, such as the email address of that account, and that can be their partition key in DynamoDB. And then they can go ahead and modify the items depending on whatever policy you wrote using fine-grained access control if you want to give credentials all the way down to the client. Now, with any AWS service, we want you to follow the principles of least privilege. Give the smallest amount of privileges that are required. If you're unsure of how many permissions to provide, there are some ways you can go about this. For example, you can create an IAM role and provide administrator access, and then use the AWS Access Analyzer, AWS IAM Access Analyzer, which will look at the CloudTrail logs during the time period that you specify for that role, and create a recommended IAM policy based on the API operations that you called. This can greatly simplify the process of applying least privileges to a principal, such as IAM role or IAM user. We suggest you protect against sensitive operations by creating roles. As mentioned earlier, in the event of a DevOps engineer, maybe allow them to do table modifications, or perhaps create a role for CloudFormation for table or for CloudFormation stack creations, saying that any modifications to the tables must come, meaning the update table, delete table stuff must come from CloudFormation. Now, we also have a feature called deletion protection. You can enable this on the DynamoDB table. So anyone who can call update table as of now could enable or disable deletion protection, but it does provide one extra step from accidental deletion of a table. Now, naturally, common recommendation is consider splitting workloads, dev and test, or dev, test, and prod into different AWS accounts. And that will separate the impact or the surface area. Also will assist with data management. For example, data backed up or data restored in the dev account is only dummy data, not real production data. Now, when we talk to customers, we hear things like, hey, I want to know if someone's accessing this DynamoDB table from outside of our IP range. Like, for example, an employee might want to read an item from a table belonging to a famous end user. Sometimes these DynamoDB tables have important information, like such as credit card information, encrypted credentials. So we want to be able to know if there's any modifications, any get items, or so on. So DynamoDB supports logging of data plane activity using CloudTrail and DynamoDB streams for that matter. So the way this works is you can specify the table RN, or just provide a list of all tables in which you want to monitor. And when you create your data trail in AWS CloudTrail, all of the control plane operations will be published into an S3 bucket for you to process later on. Once you're in S3, you can use a service like Glue, write your own Glue ETL using something like PySpark, and look for the interesting events that matter to you, such as calls outside of an IP range. Let's look at what these records look like. Inside of the data plane record, you will see the ARN of the user who made the call. This is the identity. You also be able to tell basic stuff like what time was this record made, what was their access key, and was an MFA used for the call. It will include the name of the API operations such as getItem, their source IP address, and the user agent. User agent has information such as the SDK version. As you can see here, it says AWS internal. That suggests that this was made by something like the AWS console service or maybe AWS CloudFormation, because that is an internal version of the AWS Java SDK. We also include some interesting information such as the table name and the partition key and the sort key of the item, along with all the other operations or information you see here, such as whether limit was provided, the attribute names, whether consistent read was set. Note that this data, although it can be encrypted in S3, is technically copied over from the base table. So if you have a very sensitive partition sort key, be aware that that will be copied over into the CloudTrail logs for data plane once enabled, if you're willing to pay for it. We'll also include some basic information about the response. Maybe we returned an error back, that will be here. As well, you'll receive the request ID. That is the actual request ID that you can use with AWS support, which is very helpful for us to understand what the source of the call, what happened on the API call. We have a little bit extra information, not much. Now, data written by CloudTrail into S3 can be encrypted using whatever option you choose in the S3 bucket. However, as we showed you in those log entries, those partition keys, sort keys will be in readable format once you decrypt them, pull them out of the S3 bucket. Now, if you want to store those in encrypted format using your own key or even our own key, the AWS owned key, you can do that with our built-in, by default enabled encryption. DynamoDB offers encryption at rest wherever data is stored, from the stream to the backups. You can use either AWS owned or managed key options. It is transparent. It's on every account, on every table. It cannot be disabled. AWS owned comes at no extra cost to you, no modification to the application either. If you want to go with managed keys, it does take a couple extra steps, and that can affect latency in that case, and we'll discuss that in a little bit. Now, one important thing to note is that partition keys and sort keys, if you look on our documentation, we never quite mentioned that those are stored in encrypted format in all places. In the event of the sort key in particular, the sort keys can be stored in plain text in our metadata. So be aware that although you can encrypt the entire table, sort keys, because they are used to identify partition boundaries between partition 1, 2, and 3, for example, they can be used. We do need to have their plaintext value, because when you say, hey, I need to get where user ID is equal to 1 and the sort key is between a range, we need to know which partitions are responsible for that subset of data. So for that reason, sort keys can be stored unencrypted in our metadata. Now, technically our metadata is encrypted, but it is in a way also plain text. So, that's a kind of a semantic thing. A lot of times with encryption, it's like, yes, it's encrypted disk, but I can call the get item and I can get the item back. So was it really encrypted? The answer is yes, it was encrypted. It's also encrypted in transit for that matter. But let's discuss some important considerations. Now, you have three options with keys. You can go with the AWS owned key, the AWS managed key, or the customer managed key. Broadly, the two categories are AWS owned or managed keys. Now, managed keys are decrypted, and we verify that we can decrypt them, that your IAM user has the power to decrypt them. And this is done every 5 minutes. So although data is encrypted at rest, we need to make sure that the caller has the ability to decrypt. So it is important as a caller, which is identified by your access key, that you have a long-running connection, that you don't close connections after just one request, because we like to cache that KMS key. So if you are calling DynamoDB but handling connections poorly, closing them quickly, not maintaining the connection pool, then you will have a lot of KMS decrypt calls for the AWS managed and customer managed keys. So be aware of that. Good connection handling is very important. I have had customers who have contacted us because the KMS costs are higher than their DynamoDB costs because they went the managed key option. Now, what's the difference between the managed key and the AWS managed key and the customer managed key? Well, the AWS managed key is a common key inside of KMS, your KMS account for all your tables in that region. It is managed by AWS. It's a common key. Now, customer managed key is like a custom key. So it is a CMK made inside the KMS service, but you can make one for every table. So you make one key for this table, one key for this other table, and then you can also change the key out if you need to. We use envelope encryption, so at any point you want to change the key option, you can go ahead with effectively no impact to your request or to your latency. Let's discuss gateway VPC endpoints for DynamoDB, aka VPC endpoints for DynamoDB. VPC endpoints bring DynamoDB inside the VPC, whereas before you needed an internet gateway or external internet access from your VPC out to the quote-unquote internet. Now you can use DynamoDB VPC endpoints. You create them, add them to your VPC, update the route table for your quote-unquote private subnets, and then those will be all the application instances, including AWS Lambda functions that happen to have ENIs going into that VPC, will now be able to access DynamoDB. This means you can add DynamoDB just like you would Amazon S3 or other services that have endpoints without needing public internet access. Now, note, these are called gateway VPC endpoints. This is an older version. At the time of this presentation, gateway VPC endpoints are what we offer. Now, some things to consider. First, while normal charges apply for NAT gateway access, there's no additional cost for using VPC endpoints. Second, with VPC endpoints, you do not need any IGW or NAT gateway or NAT instance. Third, VPC endpoints offer a simplified network configuration. It's going to remove the need for setting up and maintaining firewalls to keep your VPC secure. And finally, you can use IAM Policies to allow DynamoDB access through the VPC endpoints only from specific networks, IP ranges, or things like that. So you don't need to modify any of your applications. You just update the route table, point it towards the DynamoDB VPC endpoint, and there you go. Now, let's do a quick overview of some of the ways you can log and monitor security on DynamoDB. There's a lot underneath each of these services, so we're just going to kind of cover the high levels. So with CloudTrail, you can log really all operations: create table, delete table, update table. Those are provided or stored in standard trails on CloudTrail. Or you can go with the data plane logging and pay a little bit extra, and you can get all the put item, get item, and query operations. CloudTrail will record times, users, source IPs, event types, all that, and it's going to store those logs in S3. The logs can also be sent to CloudWatch Logs, although there is a limit in the entry event size of 256 kilobytes. Now, the ASConfig service is going to be able to track resource configurations over time. So, for example, if you want to make sure that all your tables have PITR are enabled, ASConfig has a rule for that, and you can go there and see what the state of your tables are. Are they backed up? Is there PITR enabled? Is encryption at rest enabled with a certain feature? All that is possible. Now, Amazon Event Bridge is going to allow you to watch for events of interest, table deletions, creations, updates, or authorization failures. You can set up Event Bridge rules that send notifications or perform actions. Finally, there's AWS Security Hub. A Security Hub uses config rules. Those config rules can do things like look for whether PITR is enabled and whether following best practices. It provides a comprehensive view of your security state in AWS and helps you check that your environment complies with security industry standards and best practices. It has controls for scaling, point-in-time recovery, encryption at rest, and that. AWS Security Hub provides you with a comprehensive view of your state in AWS and helps you check your environment against security industry standards and best practices. It allows you to check your account for scaling, whether all scaling is set up, whether there's encryption at rest in DAX, whether it has backup plans, and things like that, including point-in-time recovery. AWS Security Hub does rely a bit on AWSConfig. So with these services, you can log from left to right. You can log everything that's happening. You can be notified when things change. You can look for API operations that are of interest to you. And you can compare your resources against industry standards. Now, let's discuss some important things to know between the two capacity modes. And this is a operational best practices presentation, so we're not going to go too in depth about why you would choose one capacity mode over the other. In 2012, when DynamoDB launched, we had provision capacity. It is the most cost-effective option if you can make it work. It is technically cheaper per capacity unit if you were able to perfectly consume it every single second compared to the on-demand mode. In provision mode, scaling comes from the service application autoscaling. What I suggest is that if you're launching a new service, you try to launch with and continue to use the provision mode. The best way to move to provision if you're on-demand is, in my opinion, to look at 1-minute data points and set your minimum scaling capacity to near that point. Even if you use 1/5 of your provision capacity, you're still saving money over the on-demand mode. Now, on-demand mode does not solve the problem of hotkeys. You can have hotkeys in either mode, and the systems to split out hotkeys to their own partitions run on each service. A hotkey is where one key has a higher key frequency use, where we're just seeing more requests. Keys sit on partitions, and we desire partitions to go up to about 1,000 units per second. Now, if you go with on-demand mode, on-demand tables take about 30 minutes or so to split after you hit 50% more of your previous high watermark. So, due to delay in scaling, many customers choose to pre-partition their on-demand tables. Let's discuss that. When you have a on-demand table and you have an upcoming event, you need to go to, let's say, 100,000 write capacity units. Now, first, what you make sure is your account limits are in order. Once your account limits are in order, we're going to start with our first API call. Ideally, we're going to be able to create a brand new table with the new capacity that we expect the table to go to. But if not, we're going to update the table and set the capacity mode or the billing mode to provision with the ideal throughput. The throughput is about what we're expecting, but we also want to add in a little bit of extra headroom for us being potentially a little bit wrong. Now, when this happens, what DynamoDB will do is add partitions underneath the surface. You can't see that happening. It will take tens of minutes to complete. And during this process, the table will respond normally to traffic. It is switching to provisioned mode. You will be billed at on demand, and at some point you will be billed using the provision capacity mode. And once this is done, you will have a pre-warmed table, aka a pre-partitioned table, that will be able to go up to the amount of capacity that you set before. So you're going to set it back to the on-demand mode, which is called on the API pay per request. And from then on, you pay the on-demand rates. So in the event that you're expecting a spike in traffic to a set amount of throughput, pre-warm the table, pre-allocate the partitions by saying provision mode and then returning it back. Now, let's say you're in the provision mode. Provision mode uses application auto-scaling. And if you're expecting a spike of traffic in that, what we would suggest is you schedule this. So you can use application auto-scaling to put a scheduled action. At some point in the future, you can set what the minimum capacity would be. The service is DynamoDB. The target is the ARN for the table, or it's a specific ARN. And if you have these regularly scheduled imports or backfills or a large-scale event coming, maybe it happens in a regular schedule, you can set it. Be aware that these scheduled actions can have start and end times, so basically effective date ranges. So if there's just a holiday season coming up, you can set these actions and they will only run at the times you specify using the cron schedule. Now, let's say you are unsure which capacity mode you should use. Pull out your phone and check this out. This is a GitHub link to the Amazon and DynamoDB tools repo into the capacity mode evaluator package. The table capacity mode optimization tool will analyze your DynamoDB table usage and simulate auto-scaling behavior based on the parameters and generate an analysis to help you choose between the capacity mode. Should you go with on-demand? Should you go with provision? What kind of capacity modes should you have or settings should you have? Use this tool, and it will use your CloudWatch data to help make this decision. As I mentioned earlier, regardless of which mode you use, we still have partitions underneath, and we still have the same throughput limits, which is 1,000 WCUs or 3,000 RCUs. This is an example of what bad Nosql looks like. On the x-axis, we have time. On the y-axis, we have partitions. There's about 16 partitions in this table. As the colors go from blue to red, the amount of heat or requests increases. In this case, we see one very hot partition and one warm partition, while the other partitions are idling. In this case, we can have throttling. Now, DynamoDB does its best to adapt to this. If we have an imbalance in access, we'll split out keys to their own partitions using split for heat, but that's not always going to happen. Depends on the scenario and the behavior and the request pattern, and we may or may not split it out. But the event this is happening, how do we identify what's happening? How do we find, say, what the hotkeys are? So first, we're going to talk about the CloudWatch metrics. Now, here's the metrics to consider. For every read or write throttle operation or throttled item, every item, there's going to be a read or write throttle event. Whenever 100% of the API of the items are throttled, and which means that the whole API operation is throttled, we will emit a throttled request metric. Now, when a GSI is backfilling, we have the online index throttle events. So every single throttled item during a GSI backfill will appear in that metric. And finally, when you're using Kinesis data streams, if your stream is under provisioned, we will emit a throttled put record count. Now, admittedly, throttled request and read throttle, write throttle events, those really match with the graph I showed you earlier, the heat map. That's what that thing was called. And I just put the Kinesis data streams and the GSI backfill metrics in here because I couldn't figure out where else to put them. But on that note, I will take a second to talk about Kinesis data streams one more time. In the event that you don't have enough shards, you will get a throttle back. We'll retry for up to 35 days to put the records into your stream. Please make sure you're monitoring your CloudWatch metrics and you have sufficient number of shards on the Kinesis data stream. Now, how do you get something looking like that heat map, but that's much more specific? Well, enter CloudWatch Contributor Insights for DynamoDB, CCID. CCID provides key graphs, key frequency graphs, with the partition key and sort key for both admitted and rejected requests, throttled and accessed keys. And by using CloudWatch Contributor Insights or DynamoDB, you can figure out which hotkeys you have, where they are, identify the source, and then hopefully go and modify your application or do upstream throttling in the event that these are unexpected access patterns. So if you have throttles, enable CCID. You can do this on the base table or the global secondary index. Please note that once disabled, once you turn it off, the metric data disappears. So when you disable CCID, the graphs go blank. So make sure you get your screenshots while the requests are coming in, because when you turn it off, won't be there anymore. Now, we'll talk more about access, some important things, and we're getting here towards the end of our presentation. So we're going to discuss kind of item size, maybe updating items, and then kind of go towards a wrap up. So if you're still with us, let's talk about item size. We have noted that with higher complexity attributes by kilobytes or number of attributes inside the item, approaching even hundreds of attributes, the client-side latency is higher. This makes sense when you think about it. You need more compute time to do this JSON serialization. DynamoDB does use JSON on the body of the request. There's also the service time, the network transmit time. So if you can make your items smaller, if you can make them less complex, benchmark that, and you might find the latency is much lower. Know your item size and make sure you make each item as small as possible. Use this item calculator. There are a couple different ways to calculate item size. I still prefer the Zach Charles calculator because it's available on a GitHub page. You can just paste your item in, immediately see about how many bytes that would be in DynamoDB. He's not sponsored by Dynamo. We haven't verified his code directly, but it seems to be about right to determine item size. Identify how large the items are, and then maybe write them with your code, time that, and see how fast it takes. Let's say you have some large items and you need to lower your write cost or offload this someplace else. Let's discuss some strategies. Now, the first idea in the event of frequently updated data is to separate the frequently updated data from the bulk data, the metadata, so to speak, and put it in a separate item. So in this example here on the bottom of the slide, consider a game player's frequently updated ranking in an online game. For user ID number 1, his ranking might change from 1 to 2 to 3 and so on. If you include the game history, all the metadata, this item in this example would be 2.5 kilobytes or about 3 WCUs. Now, to update even the ranking, you still have to pay 3 WCUs. However, if you move the ranking to its own item, the consumed capacity to update that for a small item under 1 kilobyte is just 1 WCU. Meanwhile, the game history is maintained in a separate item. So consider breaking a large attribute out onto its own item so that update costs are lower. Regardless of whether you're changing 1 byte or 100 kilobytes, you have to pay to rewrite the entire item. The second thing to consider is compressing large attribute values. Instead of storing all of your data under a map data type, on the client side, you can serialize it, gzip compress that, and store that with the binary data type. So switch from map to binary data type, pick your own compression algorithm, compress the attribute, write it into the item. Now be aware, you're of course not going to be able to select attributes inside of that gzip without decompressing on the client side, and there is some client latency added to do the compression. In addition, you'll probably need to write an extra attribute mentioning the compression algorithm that you use. Now the third option for large items is to consider storing that large data in S3. DynamoDB becomes the metadata, the lookup table for the data in S3. Put the item into the bulk of the data into S3. Get the key, perhaps the version along with the bucket name, store that into a DynamoDB item as an attribute. Now, the last thing I'll leave you with is this kind of theory on bulk updates. So operational best practices, a lot of times this means we need to modify data in place. What are some things to consider? I'm not going to give you a solution, but I'm going to give you some ideas. So let's say you need to backfill a GSI attribute because you just added a new GSI. Maybe you need to remove PII information. Data is all of a sudden secret. You need to remove like first name, last name. Maybe you need to add a TTL attribute. What are some ways that you can go about this process? Well, if I could put it simply, you need to acquire the keys and then modify the data. Acquire the keys, modify the data. It can be as simple as 2 steps, but there's a bunch of services on here, so let's discuss. There's kind of 2 broad ways to acquire the keys for your table data in DynamoDB. The first is to use the native export to S3 feature, which will put your table data into S3 into your bucket in either Amazon Ion or DynamoDB JSON format. Once in S3, you can use a service like Amazon Athena to select star from that table and then get the primary keys out, the partition and sort key. Get the keys for the table. Often that's one of the hardest parts. Table exported data can quickly be indexed or added to a Glue data catalog table and then queried via Athena. Now, the other option to acquire key is to scan the table. You would, of course, use segmented scans, also known as parallel scans. You do those by providing segment and total number of segments, breaking up the table into many logical pieces. And then you scan the tables, get the keys, and then do something with them. So acquiring the keys, those are two options. Export the table or scan the data. Either export out the back door or go to the front door and scan the service, scan the front end of the table, the DynamoDB API. Then you need to figure out how to modify the items. So if you go with the AWS Lambda function, you can point it to, say, an object in S3 with the table keys from the exported data. Or you could have the AWS Lambda function scan the DynamoDB table. The other option is Glue. So Glue can work with the native exported data. It has a connector to read the exported data, or you can tell Glue to scan the DynamoDB table. Given the native support for the export option, I would just use Glue's connector for the exported table data and skip the whole scan process, which of course would use read capacity for scan and potentially impact read operations on the table. In my opinion, better to just use the exported data. Now, from there, AWS Lambda and Glue can directly write data into DynamoDB, making the modification that you require. As well, if you wanted to, you could queue up those changes. You could use Amazon SQS, the ancillary service. So you could take the item keys, put them into SQS queue, then attach the Lambda function to that, thereby decoupling the read operation, which would be the S3 data or the scanning data, reading those keys, decouple that from the write operation by putting a queue in between two different Lambda functions. You could also do the queuing up of the process into the SQS queue and then delay the writes until a later point in time using Amazon SQS and the standard queues. Now, with AWS Glue, the operation is kind of a lot more straightforward. You'd most likely be doing a read and then immediately a write, writing data directly into the DynamoDB table. It's my understanding with Glue that in most cases you're going to be using a data frame, which will be a batch write item, which would be a full item replacement. However, you can write code to do conditional updates with AWS Glue. Now, with AWS Lambda, if you're writing your code there, of course you can do conditional updates. You can say update item so long as the version number is equal to X, just to make sure you're not overwriting any kind of previous changes. Now, I also added step functions on here because if you're trying to orchestrate this entire system, you want to manage it, you could create a step function workflow. That way you have traceability, repeatability, logging, all that great, awesome stuff. Now, that is it. That is a lightning talk, if I've ever heard of it, covering everything I could possibly think of from a decade of experience on DynamoDB. And thank you for listening to my talk on the operational best practices for Amazon DynamoDB.